In the manufacturing of satellite solar panels and wings, there's a need to do non-contact, quick quality control testing to look for defects such as cracked solar cells and shunts. There's a need to test things such as trays of incoming kicks or solar cells, or the solar panels themselves, or after the solar panels are mounted onto a wing, which is often arranged in a vertical orientation. The CellSpot tool is one of the tools that BrightSpot Automation offers for the satellite solar panel industry to look at defects such as cracked solar cells and shunts in solar cells and solar panels. It has multiple use cases. In one use case, you can load product through the front door. For example, a tray full of cells or kicks can be simply loaded inside. Or if you have a solar panel, you can load it underneath. And if you have a larger panel that can be imaged at one point in time, you can actually move it around and image it in pieces. Finally, the whole structure can be rotated 90 degrees and pointed to the side to image a satellite wing that is hanging vertically. Companies often will buy boxes full of plastic trays containing many solar cells made of either silicon or 3-5 multi-junction technology. These happen to be the 3-5 multi-junction, the most efficient type. This is the type required on any US military type satellite. And they often come already with a very thin layer of cover glass on top. So these are called CICs, Coverglass Integrated Cells. And before any company wants to actually start building their solar panel, they want to make sure that there's no damage to these. And you can see in this case, there's already some wires that have been welded onto the cells, and the welding process can, if not done correctly, can result in some cracks at those weld spots. So we want to be especially careful about examining those weld spots. So what we're going to do is image those using photoluminescence technology. To take an image, I'm going to press a button on the screen here. The LED lights go on very briefly. The camera takes an image, and then we have the resulting image here. Here you can see an example of a weld crack. Here's an example of another type of edge crack. And if you want to, you can look at the original source image, which we then cropped and enhanced the contrast of in the processed image. Here you can see our Impel software running. Impel is a common software we use in all our systems. It controls the camera, it controls the power supplies, and it takes those images and then enhances them in post-processing, and we can even do AI defect detection to find all the problem areas. I'm going to show you now what it looks like when I turn on one of the LEDs in the system. Some companies will buy already formed panels and then integrate them into larger structures or into a wing. Prior to starting that integration, they want to make sure that they have good product with no cracked solar cells. This particular technology here uses standard terrestrial silicon solar cells, but the panel's made in a different way than you would for terrestrial applications so that the panels can withstand the rigors of space. What we're going to do here is test these in a non-contact method with the CellSpot tool. This tool could also be used for a company at a later stage of processing. If they bought their own cells and made them into solar panels, they could likewise use it for that application. So to do the test, we're going to merely place the panel on this sliding tray, move it underneath the CellSpot, and then start the test. So when I press the button, the LED lights go on, for a few seconds and the camera's taking an image. Then that image is processed by our software, and you can pan around and see defects such as that impact defect or that edge crack out there, another sort of impact. You could also see the original image prior to the contrast enhancement. Here we've oriented the CellSpot tool in a horizontal orientation pointing to the side to image a vertically oriented satellite wing. We don't have a real satellite wing, but we've mocked one up here with a terrestrial solar panel. So we're going to show you how we can image this in pieces with the CellSpot tool. So here we're going to start and go to the Impel software and take our first image. It's going to turn on the LEDs and take our first image. Then and we'll first take a look at that on the screen. So that first image is done, and you can see here that we can see a variety of defects and a variety of cracks, isolated areas. And now what we're going to do is pull the system forward to a different orientation. And we'll image another section of the panel over here. Again, press the button, the LEDs go on, the camera takes the image, then the Impel software will enhance that image. And here you can see we have some different area of the panel that we've not imaged. So depending on how long the wing is, you can go along and image it in pieces this way with the CellSpot tool or with our larger Plus Spot tool. Metrology is critical for the satellite PV industry to lower costs, improve performance, and reduce emission risk. BrightSpot Automation offers a suite of tools that can be used at every stage of solar cell or kick processing, panel manufacturing, and integration. We also have photoluminescence and electroluminescence tools that can see defects such as cracked solar cells, shunts or shorts, and wiring or interconnect problems. We have also methods to look at cover glass cracks and to look at the voids between the cover glass and the solar cells. We have automated AI defect detection software that can automate the process of seeing those defects and even grading the solar panels or solar cells based on figures of merit such as density of defects, length of various defects, area of defects, or darkness differences. We customize our solutions to whatever your need may be, so if you have a need for defect imaging, please come to BrightSpot Automation.